All right, good morning, everyone. Sorry I'm late. I forgot my charger here and my laptop's almost dead. So up here at the front table are the exam 1 correction. If you want to pick those up, you can. You can wait till after class, up to you. And then also exam 2's up here as well, if you did not get that last time. All right, we ready? You doing all right? We're going to start with a quiz problem that I want you to take home and turn in next class. All right, so it's a take-home quiz. And so the idea of this is not to make this a nightmare for you. I want you to take your time with the problem. Where is it? Hold on a second. It was the one I showed y'all. Come on, Robert. Okay, so it's this one right here. Now, if you want to take a picture with your camera or with your phone, you can. Maybe just zoom in a little bit more. Maybe not that big. It's that first one, A. All right, everyone got it?
What is this for, I'm sorry?
This is a quiz that is due next class. At the beginning of class, you'll turn it in. So it's a take-home quiz. I do not mind if you work together. What I don't want is one person to figure it out and then share that with everyone else, okay? I don't care if you sit together, but at the end of the day, you need to understand how to do these problems, right? So the next test, like I told you, is going to have several problems to choose from, but you'll have to do more than one. So you can't just get good at one type of problem. You have to be ready for different types. So this is a problem that requires, you know, the geometry of this problem is pretty straightforward, but just see how you do with it, all right? So that's due next class, beginning of class. Yep, okay. Get with me after class, I'll show you, okay. All right, so today we are actually starting a new chapter. We are putting to rest the related rate word problems for now, okay? So we're going to get into chapter 3, which I have here, and we are going to spend some time. The name of the chapter is inverse functions. That's actually not too important in terms of, we're really not going to be spending all of today talking about inverse functions. We're going to be talking specifically about exponential and logarithmic functions from college algebra. If you think about what we've studied so far, like learning the derivatives, right? We learned all the rules, power rule, we learned product rule, quotient rule, chain rule. We've done implicit differentiation. We've done related rate word problems. We have avoided exponential and log functions, right? We've talked about trig functions, derivatives of sine, cosine, tangent, but never have I talked about what the derivative of an exponential or logarithmic function is. So the goal of today is for us to understand what the derivatives of those are, and then once we get through that, we'll talk. I'm not quite sure if we'll go to 3.5. I probably will touch 3.5. 3.6 is really kind of an optional thing. I normally start my Cal 2 class by doing 3.5 and 3.6. That's normally where I start Cal 2. So I don't need to do these, but we'll just see how it goes, all right? So you ready? Let's do it. This is kind of a shift. We're going kind of backwards now to where we were when we, just imagine we're at the point where we've learned product rule, quotient rule, chain rule, okay? Forget the implicit differentiation for right now, you know, where you're like saying like differentiate with respect to time. Just treat everything the way we did before that. So I have to first review, and I will stress the word review, what an exponential function is, all right? So we are back in college algebra now, all right? Which I know is at least a year ago for you, right? Most of you. You took pre-cal first. Then before that, you had probably 14-14 or 13-14, depending on where you took it. So I expect everyone here to at least remember brief, like somewhere in your brain, somewhere in the cracks of your short-term memory, this idea of a function f of x equals a to the x, where a is some positive number, okay, and a is not 1. So examples of exponential functions, something like f of x equals 2 to the x. That's an example of an exponential function. If y'all are just coming in, I assigned a quiz at the beginning of class, so please talk to me at the end. Another example, how about we do f of x equals 1/4 to the x. Those are examples of exponential functions. The idea is that your variable x is up in the exponent, and the base is a number. So do not confuse this, right? It is not this. This is a polynomial function because your x is in the base and the exponent is a number, right? You see, it's like they switch places. This is an exponential function. This is a polynomial function. We are interested in these right now. And so, does this look familiar to you? Yeah? Exponentials? Okay, so what do the graphs of these look like, right? We need to just make sure we understand what the graphs look like. So I have an illustration here of what the graph of an exponential function looks like. This is kind of a general picture. This is what they look like if a is greater than 1. So if the number down here, the base of the exponential function, if that number is bigger than 1, then we should expect to see a graph that looks like this. So what are the things that you need to be aware of in terms of this graph? First of all, everyone should understand that this graph is always above the x-axis. So it's always positive, right? You're never going to get a negative here. You're always going to get a positive output. The other thing to realize, let me zoom in so we can see this a little better. The other thing to realize here is that when you're looking at an exponential function, I'm trying to erase the function. With the a being bigger than 1, okay, right now a is bigger than 1, then in terms of a limit, if I say what's the limit as x goes to infinity, I'm saying what does the function do as we go that way? Well, where does it go? Up to infinity, right? So does this limit make sense to you? That as x goes to infinity, the function goes to infinity? Yeah? On the other hand, if I ask you what's happening to the function as x goes to negative infinity, now I'm asking you to look at it as you go that way, right? And what does it do? It dives down towards the x-axis, which means getting smaller and smaller and smaller. So it is approaching, right? It is approaching this horizontal asymptote, right? So it is getting smaller, it's approaching 0. So does that limit make sense to everyone? Yes? Okay, that's when a is bigger than 1. What happens when a is less than 1, like a fraction, like 1/2 or 1/4? Do y'all know what happens to the picture? It flips over the y-axis. So here's what it looks like if you change that base to be a fraction, like 1/2 raised to the x or something like that. So it flips over the y-axis. And that changes what it does on the left and the right-hand sides, right? On the blue graph, now if I go to infinity, where's it headed? To 0. And if I go to negative infinity, where does it go? up to infinity, right? We need to understand that. Like, we need to be okay with that. If it comes up in, later on, it says, hey, what is this function doing as you go to infinity? You should be able to, like, imagine what the picture looks like and see it behaving, going either up to the right, down to the left, or the other way around. We good? Okay. Now, what are some properties of exponentials? So this is really going back into, again, the college algebra stuff. This is all stuff that should look familiar to you. We've actually used this stuff already, but this is just to remind you that if you have something to a power times something, this is multiplication, right? It's implied, times something to a power. If you want to put those together, you add the exponents, right? We've done this before. If you take something to a power, divide it by that same thing to a different power, you subtract the exponents. If you take something to a power and then raise all of that to a power, you multiply the exponents, right? This is all familiar. These are properties of exponents from college algebra. This is just a reminder, that's all. And then this next one says if you have two things being multiplied to a power, you can apply the power to each one, right? So again, none of this is new. That's it. Okay, that's it for exponentials. We know what they look like, and we know the basic properties. Now, all exponential, well, you know what? Before I move to the next one, there's one really, really special exponential function. You'll know which one I'm talking about? There's one in particular, because, exponential functions all look like this, a to the x. There's one in particular that you learn in college algebra that's really, you're told it's really important. Anyone know which one I'm talking about? When I put it up here, you'll recognize it. There. E to the x. Recognize that? E to the x. And you're told in college algebra that this is a very special function. It's actually called the natural exponential function. Now, what is E? What is E? Does anyone know what E is? That has to do with the inverse of this function. What is E? No. I think y'all are both thinking already of the inverse of these functions. The inverse of an exponential function is a logarithmic function. That's not what I'm asking. What I'm asking is, do y'all know what E is? It's the base, okay. But what is it? I mean, like if I write this down, what's the base of this exponential function? 2, okay. And 2 is just the number 2, right? Over here, the base is E, right? But what is E? It's not imaginary. It is a number, though. It's not imaginary, though. It's just a number.
Isn't it like 3 point something?
Okay, so pi, so we're all familiar with pi, right? Pi, yes, yes. Okay, pi is approximately 3.1415, and it has this unique property that decimal goes forever, and there's never a pattern to it. We call that an irrational number, right? Irrational means this decimal never terminates, never stops, and it never repeats itself. Okay, so that's an irrational number. But it's a very special irrational number. We use it with circles and things like that. So because it's such a special number, we give it this real nice symbol. We call it pi. Anytime in the real world human beings assign a letter to a number, it's because it's a special number. Yes. So this is actually, E is just a number, just like pi is just a number. It's approximately 2.718. And again, it keeps going forever. It never terminates and it never repeats. It is another irrational number, all right? And it's a very special one. It's so special, in fact, that we give it a letter to represent it, all right? So we all, from college algebra, should have been shown this function. And I'm sure your professor told you that e is approximately 2.718, right? So this is just an exponential function that goes which way? Like does it, if I graph it, does it do this? Or does it go the other way? So this one or this one? It should be the first one, right? Because the base here, e, is what? 2.718. And I said if the base is bigger than 1, it's going to look like this, yes? We call this, by the way, we call that exponential growth. We call this exponential decay. Not that important here, but that's what it's called. So the natural exponential function is a very, very important function. Well, how many of you were told that in college algebra, that this is really an important function? No? Are y'all okay? Yeah? It's early? Yeah. But do y'all remember, did your professor tell you like this is a really special function? You remember hearing that? I beat it into my class. I tell them it's very special. And I tell them it's special because of its properties in calculus. So when you think about all the functions we've done, right, every function we've looked at this semester, when you take the derivative of a function, you get a new function, don't you? Like if I say, hey everyone, take the derivative of x squared, what do you get? 2x, okay? If I say, hey, take the derivative of sine x, what do you get? Cosine x, right? So you start with the function, take the derivative, you get a new function, right? Take the function, take its derivative, you get a new function. I wonder if there's a function that when you take its derivative, it's the same function. Like it doesn't change to a new function, it just stays itself. Right? Doesn't that seem like a reasonable question to ask? Like, does there exist a function that is its own derivative? Right? Does that seem like something, like a natural kind of question that someone might ask at some point? Yeah? Well, there was a big question for a long time, historically. We were trying to find a function that actually behaved that way. We were like, is there a function that is its own derivative? Does it exist? Does it exist? We went looking for it, and we finally found it. And this is it. This is the function that is its own derivative. All right? So in college algebra, it's hard to explain to a student, well, it's its own derivative, because you don't know what a derivative is in college algebra. So look, we're headed that way. I don't want to get ahead of ourselves here. I just want to make sure you remember this function, that it was given to you in college algebra. All right? That's a very special one. Does anyone remember another special function that you were given in college algebra? Not as special as this one, but another exponential. It has a different base, but not base e. Anyone know? How about this one? Again, your professor may or may not have stressed that one too much to you. That one is the base 10 exponential function. And like I said, this one is like the super nice one. This is the special one. This is the only one that is its own derivative, as I'll explain more in a moment. This one is special, but not because of that property of being its own derivative. It has to do with the fact that the base is 10. And why do you think 10 is an important base to have, as opposed to like having a base of 2 or 5 or something? What do you think? Why do you think base 10 is important to us?
Doesn't it go into like log or something?
Yeah, well, yes, exactly. This will turn, the inverse of this function is log. LOG, not natural log, but LOG. But why 10? Like, why is 10 better than 8? Why is 10 better than 12? Why is 10 better than 2, right? Hmm? Cleaner in what sense? I mean, isn't our number system base 10? Y'all heard that before, right? Our number system is base 10. Do y'all know what that means? Do y'all have any idea what base 10 number system means? Would you like to know a little more about it or no? We can go off on a tangent here, but I mean, what does base 10 mean? Let's take a moment to talk about it. If I write down the number 342, we all understand what that means, right? We all understand what that means. In our number system, if we were to write down, let's just say a 3-digit number, okay? 3 digits. I get to choose something to put here, here, and here. What are my options to put here? How many options do I have? I can put 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? Those are the digits I'm allowed to put in here. There are 10 options for me, right? So let's pick a number. I'll put 2 here, all right? And then how many options do I have here? Still 10, right? So 4 here, and then I put 3 here, right? Now, what do each of these digits represent? This is how many ones I have. This is how many tens I have. This is how many hundreds I have. Another way I could say that is this. I'm going to come down here. This is saying that I have 3 hundreds, right? 3 times 100. And then I add to that, now I have 4 tens, and then plus 2 ones. This is something you would do in like grade school. Do y'all remember anything like this from the grade school? Maybe, maybe not. It's been a long time, right? But does this make sense? Okay, one more thing I want to point out. This, and this, every one of those numbers is a power of 10. Isn't this first 10 squared? And the next one is 10 to what power? 1, and then plus 2, and this is 10 to what power? 0. 10 to the 0 is 1. So our number system, the way it works is that the first digit is how many 10 to the 0s you have. The second digit is how many 10 to the 1s you have. The third digit is how many 10 squareds you have. The next digit would be 10 cubes, right? So how many 1s, 10s, hundreds, right? But it also works on the other side of the decimal. So if I put a decimal point here, and I put, let's say, 5, 3. This is how many whats I have. Tenths. Tenths. This is how many hundredths. So this is how many tenths I have, right? How many tenths? This is how many 1/100ths I have. Yeah? And another way I could write 1 over 10 using this would be 10 to what power? -1. And this one would be 10 to the -2. Do you see how every digit is just some power of 10? And when we pick our digits that we put in here, we have 10 options, right? 0 through 9. Got it? That's the base 10 number system. There are other number systems that are not base 10. Does anyone know of a number system that's not base 10 that's used in computer science? Where are my computer science majors? Computer science? Okay, so what do you know what base number system the computer works in? Binary. Binary. What does binary mean? 0 or 1, which means there's only 2 options. So imagine you live in a different universe where you want to create a number that's 3 digits long, but you only have binary options, meaning you only have 2 options. Those options are 0 or 1. See, we are base 10, so we have 10 options, 0 through 9. But if you're only allowed 2 options, then you can only put a 0 or a 1 here. So I'll put a 1. All right. Then here I can put a 0 or 1. I'll put a 0. Then here I'll put a 1. Let's just say, right? Using the same format, like this is how many 10 to the 0s. This is how many what to the 0s I have. How many options do we have? For each of these digits, how many options? 10. So this is 10 to the 0, right? So how many options do I have for each of these? 2. So this is how many 2 to the 0s I have. This is how many 2 to the 1s I have. This is how many 2 to the 2s I have. Does this make sense at all? So this is really, I have 1, 2 to the 2. I have 1, 2 to the 2, plus I have no 2 to the 1s, plus I have 1, 2 to the 0s. What's 2 squared? 4 times 1? 4 plus 0 plus 2 to the 0 is 1. 1 times 1 is 1. So what is that number for real? What is that number? 5. The number 101 in binary is actually the number 5. Yeah? How many number systems are there? As many as you want, right? You can have base 2. There's base 8. The common ones are base 2, base 10. Why does a computer use base 2? Anyone know why a computer uses only 2? That's a bigger question. Why does a computer only use zeros and ones? It's on and off. All a computer ever knows is on or off. That's it. A computer either recognizes that there is an electrical signal there or there is not an electrical signal. If it's not there, it's a 0. If it's there, it's a 1. So when we sit there and we're sitting there streaming some 4K video on our phones while we're driving down the road, it's hard to believe how many zeros and ones are floating through the air. Like, it's amazing how much information, zeros and ones, are actually just flying around us right now. You can't see it, it's right, it's all, but it's crazy because all our phones know is on off. That's it, on off. Every little pixel on your screen that comes on and off, right, is just a switch. So, okay, we're getting way too far out there. So, we could spend 3 weeks on different base systems. So we use base 10, right? Humans said at some point, we all said, hey, you know what? We're going to use these digits. Right there. Every number that we create, we're only going to use those digits right there to create the numbers. There are 10 options for each place of the digit, or each position of the number you write. You only can use those 10 options. Why do you think that we use base 10 and not base 2 as human beings? Why not use base 8? Why not use base 2? Why not use base 16? What the hell would base 16 even look like? Right? Any guess as to why we use base 10? It's a simple answer, but it's so simple it's like an elusive answer because it's simple.
Is it because of the zeros at the end?
It's simpler than that. Think about something unique about us. We've got 10 fingers. We've got 10 fingers. So it makes sense for us to only use 10 digits, right? Those 10. I promise, I would bet my life, I would bet my life that if we had 8 fingers, well, we need the thumbs or we're still scavenging out there, right? We need the thumbs. So let's just say we had 8 fingers. I'd be willing to bet my life we would use base 8 number system. And it would look normal to you because that's all you would ever have known. But we use base 10, it looks normal to us because we have 10 fingers, all right? There is another base system. Has anyone ever seen that movie, Martian, with, what's his name? The guy that gets stuck on Mars. Matt Damon. It's kind of an older movie, I guess, but he's trying to communicate with Earth, and he's limited in how he can do it, and he realized, I'm going to use hexadecimal. That thing where he does the little thing? Yeah, so he uses hexadecimal, which is base 16, is a base 16 number system. So in base 16, you have 16 options for each digit. So if you write, let's say you write a 3-digit number in base 16, then I have 16 options here, 16 options here, 16 options here. So that does not mean 0 through 15. That's not, because 15 is not a single digit. So what we use in hexadecimal is we start using letters. A, B, C, D, let's see, 10, 11, 12, 13, 14, 15. In hexadecimal, you are allowed to use those as your digits. So in hexadecimal, you can actually have this as a number. B, 3, C. That is a number, in hexadecimal number. What does it represent? This is the last thing I promise. We're going to move on. This is how many whats I have. Think about this. This is how many 16 to the zeros I have. Why 16? Because there's 16, we're base 16. This is how many 16 to the ones I have. This is how many 16 to the twos I have. With me? Yes? Okay, now this means I have B 16 squareds, plus I have 3 16 to the first powers, plus I have C 16 to the zeros. You all still with me? Okay, let's start from the right because this is the easier one. 16 to the 0 is 1, right? C is really what for us? 9, 10, 11, 12. So this means I have 12 ones, okay, 3 16s. And over here, B is really for us what? 11. This is 11 16 squareds. And if you just do all that together, that is the number, that is what that number truly is in our base 10 system. I hope that makes some sense, all right? The point is, of all of this, is that f of x equals 10 to the x is a very important exponential function because it's the base 10 exponential function, and base 10 is the number system we work in, and so that, of course, is going to be an important function, right? The base 8 is exponential. It's just not as important as this one because we don't use it for our number system. Okay. I need to move on. All right. All exponential functions, when you graph them, we just saw they look like this or like this, right? It's one or the other. So if I tell you to look at those graphs, are they functions? Yes. How do you know? Pass the vertical line test. Do they have inverses? Yes. How do you tell? How can you tell they have inverses? Functions, you test the vertical line test. To see if they have an inverse, horizontal line test. So if I draw horizontal lines, I never hit that graph more than once. Same with this one. I never hit it more than once, which means both of these, well, all exponential functions have inverses. And their inverses are the log functions. Okay, so that's the next thing we need to recall from college algebra, is what the log functions look like. So let me put first up here what a general log function is. If you have f of x equals log, you write log, you put a subscript a, you put x. That is your log base a function. Here's what a log function looks like. And I'm going to zoom out a little bit there. Nah, that's too much. This is what a log function looks like if the base a, that base right there, if it's bigger than 1. This is what it looks like. It's different than an exponential function, right? It's different. What happens as I go to the right? This is real important. My Cal 2 students, I still have to slap them every once in a while with this stick to get them to remember this. When you're looking at a log function, as you go to the right forever, where does the function go? Infinity.